Welcome to Focus 4 of Space, and this is looking at light. And there were 3 or 4 things that happened early in the 1800s and 1900s which changed our understanding of light, mainly what Einstein figured out about light. But going right back, originally there was a lot of debate about whether light was a wave or a particle. In the 1800s, Thomas Young showed that light or light rays could interfere with each other, and interference with the wave property, which suggested that light was a wave. A man called James Clerk Maxwell, probably one of the most famous physicists and important physicists of all times, showed that there's these special sort of waves called EM waves, and they existed of electric and magnetic fields, and if they went through space, they'd have to travel through space at a speed of 3 by 10 to the 8 meters a second, which at the time was pretty close to the measured speed of light, so he figured out that light waves were these special forms of EM waves, and then other scientists like Helmholtz and Hertz actually showed there was other EM waves apart from visible light, such as radio waves, etc. And this posed a little problem though, because at that stage it was known that all waves had a medium, and if light was a wave, the big question was, what was the medium for light? What was oscillating? What was vibrating? What was the medium through which light travelled? And that led to the concept of the ether, because even though no one could detect a medium for light, there was such a strong belief that light must have this medium, it was called the ether. And based on what they could observe, physicists inferred or figured out what some of the properties of the ether must be to explain the properties of light. And they're here. First of all, the ether had to fill all of space, and that's because light travelled everywhere. And if light could travel everywhere, that means light medium must have to be everywhere. So the ether has filled all space. The ether had to be stationary as well, and that's because light travelled in straight lines, and if the ether was moving, that would mean the light would move as well, and therefore because light travelled in straight lines, the ether must be stationary. The ether must be transparent because we couldn't see it. The ether must permeate or go through all matter, and that's because they knew that light waves could pass through matter, such as glass. Visible light passes through glass, therefore the ether must be inside glass. But X-rays can pass through other objects as well, and therefore if X-rays are a form of light and can pass through objects, the ether must permeate through objects as well. And it also had to have low density because we can't detect it, we can't weigh it, and also have great elasticity because light could travel great distances without losing energy. So that was the proposed properties of the ether, the medium for light, based on what we knew about light. But even still hadn't been detected. And one important concept is something called a frame of reference we're going to look at now. The ether was in fact the ultimate frame of reference, okay? And what we mean by a frame of reference is a fixed reference point to which we could measure motion. And if the ether was light's medium, and we know that light travels at 3 by 10 to the 8 meters a second, that meant they proposed that light travelled at 3 by 10 to the 8 meters a second relative to the ether. So the ether was like this ultimate reference frame in the background of the universe from which all motion could be measured relative to the ether. Now, a frame of reference is defined here. This is something we need to know what it is. It's very important for physics. A frame of reference is a provided set of axes from which an observer can measure the position and motion of all points in the system, and as well as the orientation. But we can stop there for our definition of what a frame of reference is. So often, when we're doing experiments, we use the Earth or the classroom as our frame of reference. We assume the Earth is stationary or the classroom stationary, and we decide if some point in the classroom is going to be the 0 point, and we can measure our displacements and velocities and stuff relative to that particular point. So that's our frame of reference. You might have also some other frames of reference. For example, if you're travelling in a car at constant speed, you feel like you're stationary inside the car. You know you're going 50 kilometers per hour, but relative to the car, which is your frame of reference, you're travelling at 0 kilometers per hour. Someone might overtake you though in that car, and if you look out your window, you see them travelling relative to you at 10 kilometers per hour, and that's according to your frame of reference. But there's other frames of reference as well, because someone might be standing on the side of the road. So here's a pedestrian standing on the side of the road. They're travelling at 0 speed. Here is your amazing car travelling at 50 kilometers per hour. Although to you it looks like they're travelling at 0 kilometers per hour. Another car goes past you. Now, according to you, it looks like they're going forwards at 10 kilometers per hour, but as far as the person sitting on the side of the road is concerned, that car's probably travelling at 60 kilometers per hour. So there's different frames of reference. We have a frame of reference which is the car, a frame of reference which is the person sitting on the side of the road. It doesn't matter what you choose as your frame of reference, it just means that your measurements might be slightly different depending on what frame of reference you're choosing. Another example of frames of reference we've looked at so far is Galileo's experiment. He dropped the ball from the ship's mast. Remember, he had the ship, and the ball was dropped from the ship's crow's nest. It's a pretty bad ship here. And the ship was travelling at a certain velocity, and when they dropped the ball appeared to land directly beneath the mast. What actually happened though, according to the frame of reference on the shore, was if the ball was dropped here, and the ship a few seconds later was there, the ball actually left here and travelled in a parabola and landed on the bottom. So it's relative to the frame of reference of someone in the ship, it looked like it fell straight down. Relative to someone on the shore, it carried that initial speed of v and then fell down in a parabola, it fell to the bottom here. So there's different frames of reference for different people, and different people will take different measurements based on their frame of reference. Little question though, what would have happened if this boat was accelerating? Something I think we talked about at the time. If this boat was accelerating, an accelerating frame of reference, something different would have happened, because the ball would have left, when the ball was dropped, it would have had a certain velocity v horizontally when it was dropped. But if the boat was accelerating, it would have got a bigger velocity by the time the ball had fallen. So it might have been traveling much faster. The ball would have actually fallen behind the mast in that case, because it wouldn't have gained that extra velocity of the boat as it was falling down. So if you've got an accelerating frame of reference, things can be a little bit different than in a non-accelerating frame of reference. And this is why in physics we're going to talk about two things called inertial frames of reference and non-inertial frames of reference. Now in the classroom, we do our experiments using the room as a frame of reference, as we said before, and we assume the classroom is stationary because it looks to us as it's stationary, but it's actually not stationary. For in fact, the Earth is travelling around the Sun at 30 kilometers per second. So that means your classroom you're in right now is actually moving at 30 kilometers per second. It looks stationary, but it's actually going quite fast. And on top of that, our whole solar system is travelling around the Milky Way at 230 kilometers per second. So at the very slowest, this classroom is actually travelling at 230 kilometers per second. But we assume it's travelling at zero because our frame of reference is the classroom. We can pretend it's travelling at zero speed and do all our experiments and measurements pretending it's actually travelling at zero speed. Why don't we feel the motion? Well, the reason we don't feel the motion is because we're travelling at the same speed as all. We're travelling at 230 kilometers per second. Therefore, we're travelling at exactly the same speed as the classroom, and therefore we feel like the classroom is not moving relative to us, and we don't notice the classroom speed is moving. But just a little thought experiment: what would happen if the room suddenly accelerated to the left? Have a think about that. If the classroom suddenly accelerated at a high speed or a high acceleration to the left, what would happen? Well, what I think would happen is the classroom suddenly accelerated to the left, but we didn't accelerate because there's no force on us making it accelerate. We'd actually crash into the right side of the classroom because the right side of the classroom would actually accelerate towards us as it's going to the left. What if it suddenly accelerated downwards at less than g or greater than g? Well, if the classroom suddenly accelerated downwards at less than g, we'd suddenly feel a bit lighter because there'd be less reaction force from our feet up on top of us. If the classroom accelerated down at g, the classroom and us would both be falling at 9.8 meters per second. That'd be like weightlessness or free fall. If the classroom actually accelerated downwards at faster than g, say at 12 meters per second, we'd actually rise up off the floor and crash into the ceiling. So as long as our classroom is travelling at constant velocity, we can't notice that velocity, and therefore we can do all our experiments, and our experiments will be perfectly fine, and the experiments will be just like the travelling at zero speed, even though we're travelling quite fast. But as soon as you have an accelerating frame of reference, weird things start happening. You start moving relative to the frame of reference. And I'm going to skip this little example here for the lift. We've already talked about that in class before. But here's two very important definitions we need to know. The difference between an inertial frame of reference and a non-inertial frame of reference. An inertial frame of reference is a frame of reference that is at rest or constant velocity. In these cases, our classroom as it is right now, a car travelling at constant speed, standing on the side of the road. Your frames of reference are travelling at zero or a constant velocity, and because they're travelling at zero or constant velocity, Newton's first law holds true. Objects in your frame of reference will stay at rest or constant velocity unless acted on by a force. While you're sitting in the classroom, you've got a pen on the desk, it'll just sit there unless you put a force on it. But the other sort of frame of reference is a non-inertial frame of reference. That's a frame of reference that's accelerating. Our accelerating classroom, for example. And in such frames of reference, Newton's first law appears to be violated because you'll suddenly fling yourself left or right or up or down as the classroom is accelerating. These things will start to move without any apparent forces acting on them, and therefore Newton's first law appears to be violated. Now we know the reason why you smashed into the right side of the classroom was because the classroom is accelerating, but inside, if you were completely trapped inside that frame of reference, it would suddenly appear as though some magical force appeared and smashed you into the right side of the classroom, even though what was really happening is the classroom was accelerating to the left. So in these non-inertial frames of reference, these apparent forces appear out of nowhere and make you move, which seems to violate Newton's first law, which is why they're called non-inertial frames of reference. So today you're going to do a little experiment for me about inertial and non-inertial frames of reference. You'll need to ask your teacher very nicely to open the prep room door, and just around the corner is a trolley with this sort of equipment on there. You need to get that out and start doing the experiment. The experiment is pretty straightforward. I've put a little video on Schoolbox which I think you should watch before you start, just to show you some of the little details about what you're going to be doing. But basically, you're doing an experiment to distinguish the properties of inertial and non-inertial frames of reference. You'll have a range of equipment as said in this little list here, and your first step of your method is to set up the trolley as shown in the diagram, and then sketch a little diagram on your page about that, and please watch the video to have a look at how it works. Once you've set up your trolley, you've got to do the following things, and there's one thing I left off your sheet, so please make sure you add that to your observation list. You need to observe what happens to the marble and what happens to the pendulum. I'm not sure I mentioned the marble on the instruction sheet either, but what happens to the marble and what happens to the pendulum in each of these situations. Be very careful when you're looking at the acceleration ones, because as you accelerate, you'll often accelerate it and then decelerate to stop, but make sure you're watching what happens during the actual acceleration specified in the list here. And when you're drawing your diagrams, you can always draw your diagrams from above or the side, but it's particularly important to try and draw your diagrams from above when you're drawing these two sets of results. There's a series of discussion questions underneath these observations or results just here. The discussion questions should be pretty straightforward to answer. Some of them we've already answered in the previous parts of this video, so if you need to skip back and write down some definitions of things like frame of reference or inertial and non-inertial frames of reference, please do so. So spend some time now and get that experiment done, and then come back and watch the rest of the video. So in your booklet, after you've finished the experiment, the next thing we're talking about is the ether wind. Now, we've talked about the ether being the supposed medium for light, that what they thought the light was a wave, therefore it needed a medium, that ether was the medium for light. But before we start thinking about the ether, I want you to think about a few questions. First of all, if you're in a car traveling along, say, the freeway, traveling at quite a high speed, and you open a window, what happens? Well, what happens is suddenly a wind appears inside the car. There's air rushes into the car. And the question is, why does opening the car window create wind? Well, really, opening the car window doesn't create wind, but the wind is stationary outside your car, and you're traveling through that stationary air. And therefore, if you're traveling at 50 kilometers per hour, you are traveling at 50 kilometers an hour relative to the wind, but also that air is actually traveling at 50 kilometers relative to you. So it depends on your frame of reference. So because your frame of reference is the car, even though the air is stationary to you, it feels like the air is traveling towards you at 50 kilometers per hour. So therefore, when you open the window, that air is hitting you at 50 kilometers per hour. That's just a silly question to get you thinking the next one there, so let's ignore that. But this is what led to the concept of ether wind, and we'll talk about why in a second. Another little thing to think about before we start thinking about the ether wind is if you had a little toy boat, and that's a pretty good picture of a boat there, that one's not so good, but you've got a little toy boat, and you put it in a stream. Now that stream is running at 2 kilometers per hour. And the question is, if you have the boat running at the same direction as the stream, or the opposite direction of the stream, and you're watching the little boat from the shore, what speed would that boat be going relative to you in both situations? Well, I would say in this case, the stream's already running away from you at 2 kilometers per hour. Your boat's then traveling at the same speed, at 5 kilometers an hour on top of that. So I'd say in this situation, the boat would be traveling away from you at 7 kilometers per hour, because the speed of the stream plus the speed of the boat. In this case, though, we've got the boat traveling upstream against us. So the stream is actually traveling this way at 2 kilometers per hour. The boat's traveling upstream at 5 kilometers per hour. I would say, therefore, that the net result is this boat's actually going to be relative to you traveling upstream at 3 kilometers per hour. And that's compared to your frame of reference. But in another question here, in both cases, what would the speed be relative to this little leaf here that's being carried by the current? So in this case, the leaf's being carried by the current at 2 kilometers per hour, and our boat's sitting on top of there, traveling at 5 kilometers per hour. Now, relative to this leaf, the boat's actually going to be traveling at 5 kilometers per hour that way, because the leaf's already traveling at 2 kilometers per hour that way, and therefore, relative to the leaf, it'll be traveling at 5 kilometers per hour that way. And the same in this situation here. We've got the boat traveling upstream at 5 kilometers per hour. Relative to us, it's only traveling 3 kilometers per hour, but in this case, relative to the leaf or relative to the stream, it's still traveling at 5 kilometers per hour. So once again, depending on your frame of reference, you might measure speeds of things differently depending on your frame of reference. So how does that relate to the ether wind? Well, because all objects such as suns, moons, and particularly the Earth were moving, it was clear they must be moving through the ether, because remember, the ether was stationary. And this meant, and let's see what that meant, this might be something to add to your notes, this meant that relative to Earth's surface, the ether will be moving past the Earth, which is the ether wind. Just like opening that car window, and therefore the stationary air rushes in because you're moving relative to it. Because the Earth was moving through the stationary ether, that meant the ether should be rushing past the Earth, which they called the ether wind. And because ether's light's medium, and light travels at 3 or 10 meters per second relative or respect to the ether, this meant in theory a person on Earth should measure different speeds of light depending on the direction they shine the light ray. If they'll shine the light ray in the direction of that ether wind, or against the ether wind, or across the ether wind, they should in theory be measuring different speeds of light, just like we measured different speeds of that boat as it was travelling different directions relative to the stream. And why? Well, it says here because depending on the direction of the ether wind, light shining in different directions will either be travelling across, with, or against the ether wind. And that concept that light should be travelling at different speeds in different directions relative to that ether wind gave two physicists, Albert Michelson and Edward Morley, an idea of how to prove the ether existed. And their idea was, if they could measure the differences in light speed when it was travelling in different directions, then they could show there was an ether wind due to Earth motion, and if there was an ether wind, there must be an ether. So that was their idea. If they could prove that light was travelling in different speeds in different directions, that means they could prove there was an ether, and that means they would prove the whole concept of the ether once and for all. But before analysing the experiment, there's one more little analogy we need to think about before we analyse their experiment. And that analogy actually comes from your textbook, and it's another boat analogy. You've got two boats, A and B, are in a 4-kilometre race on a 2-kilometre wide river. So these two pictures here were like a bird looking down on the river. The river is 2 kilometres wide. Now, boat A decides to travel 2 kilometres upstream and then 2 kilometres downstream. That'll be there 4 kilometres just to try and win the race. And boat B instead tries to travel straight across the river and then back again to be their 4-kilometre race. Now both boats travel at top speed of 5 kilometres per hour and the river's flowing at 3 kilometres per hour. So which boat wins, or is it a time? Well, let's analyse this situation here. First of all, boat A, it's travelling against the current. It looks like the current's actually going this way in this case, so the current is actually going at 3 kilometres per hour that way, and the first time it's trying to travel, it's journeying out against the current. Now the boat speed is 5 kilometres per hour through the water, which relative to the bank is only 2 kilometres per hour. The time taken is distance over speed, or 2 kilometres is the distance, divided by 2 kilometres per hour. This boat will take 1 hour to travel these 2 kilometres up the river. But then coming back again, the current's actually going this way at 3 kilometres per hour, so the return journey is with the current. So the boat speed is 5 kilometres per hour through the water, or 8 kilometres per hour relative to the bank, because relative to the bank it's got the 3 kilometres per hour plus the 5 kilometres per hour. The time is distance over speed. It's going back 2 kilometres divided by 8 kilometres per hour is quarter of an hour, or 15 minutes. So the total time for the journey is 1 hour upstream, and 15 minutes back gives us 1 hour 15 minutes. Situation B, heading across the river. Now we did this sort of thing last year. To head straight across, this boat actually has to angle itself upstream a little bit so the current takes it back to a straight line. So we can try and figure out what the speed would be. So the boat speed, maximum boat speed is 5 kilometres per hour, so it's going to be heading upstream a little bit at 5 kilometres per hour. The current's going to be bringing it back, so we can figure out how fast it's actually travelling directly across the river. And by Pythagoras, 5 squared, take away 3 squared, gives us 4 kilometres per hour. So relative to the bank, that boat's travelling at 4 kilometres per hour this way, and because it's a symmetrical journey, it'll be travelling at 4 kilometres per hour back again. So the time taken is distance over speed. The one direction journey is 2 kilometres divided by 4 kilometres per hour. It's half an hour each way. So in fact, this boat that's travelling across the current and then back again will travel only 1 hour for the whole journey. Therefore, it's going to win the race. And this is similar to the ether wind and Michelson-Morley analogy. The light travelling in different directions relative to the ether wind will be travelling at different speeds, just like these two boats travelling at different directions through the stream end up travelling at different speeds. So the Michelson-Morley experiment was an experiment to measure the presence of the ether and therefore prove the ether model. How they're going to measure the ether was by measuring the ether wind, and how they're going to measure the ether wind was by measuring the fact that light had different speeds in different directions. And that meant for this experiment they need to get light travelling in different directions. And what they wanted to do was use a one beam of light and show that when they made that one beam of light split in half and travelling in different directions, each half of that light ended up travelling at different speeds and therefore proving that the ether wind existed. So what do they have? They had their experiment on this big stone block. The big stone block was there so the experiment wouldn't change in size or warp or vibrate, so therefore it wouldn't interfere with the delicate measurements. The entire stone block was floating on a bath of mercury so they could rotate the top stone block around. And why they want to rotate it, why they want no vibrations? Well, their experiment required them to take very, very precise measurements of the speed of light, and they did that by measuring something called an interference pattern, which you can see down here. But let's look at the basics first, and then we can go into the details of what an interference pattern was. The first thing they had here at S was a light source. This diagram eventually you'll be drawing in your book. And that light source, it actually caused light to shine out of the light source, obviously. And that light hit this thing in the middle here called K. Now what K was is actually quite important. K is a half silvered mirror. And we know that silver is the metal that makes mirror shiny, and this was half silvered, which meant that half the light would go through and half the light would be reflected. So to represent the fact that half the light's going through and half's being reflected, only half is going to be reflected upwards off the mirror, and this mirror is at 45 degrees, so half of it goes straight up and the other half goes straight through. So we'll draw half that light going, well, doesn't want to go straight through. Let's try to make it go straight through again. Half of the light will be going straight through. That's much better. So this light's actually travelling, not like that, it's getting used to the system. Half the light's going straight through, half the light's being reflected upwards, and here is our original beam of light coming out. So that light has been split in two. So this wave of light has now been split into two subwaves of light. And don't forget that light is a wave. So light being a wave, it's just like, you know, a waveform, and these would be waveforms as well. Now what these things M1 and M2 are, they're mirrors, and these two mirrors are actually at 90 degrees to each other. So you get a 45 degree angle mirror in the middle and two 90 degree angles here. So what happens when this light hits this mirror, these are both fully silver mirrors, so when this light hits this mirror, it's just going to bounce straight back again. So we can represent that by the light coming straight back. So it hits the mirror, it's not orange, it's my green light, that's me. Alright, that light's going to bounce straight back again, and I'll represent that by some other arrows. If this computer lets me draw arrows. So it's going to go up and come back, and for the purple beam as well, it's going to strike that mirror and then come back. Boom. Okay, so we've got the light, original light being split in two, travelling at 90 degrees to each other, one going up and back, one going here and back. And when these two beams hit the half silver mirror, well, some of this light, this green light's going to end up going straight through, and some of this purple light's now going to be reflected by the half silver mirror again. So what we're going to end up having is this green and purple streams of light travelling down here. So there's our purple light, it's going to be travelling down like this. And some of our green light, it's not really green light, but the green beam of light I'm drawing here will be travelling straight down as well. So what they've done, just to recap, one beam of light, one wavelength of light, hits the half silver mirror. Half of it ends up going straight through, reflecting off this mirror back, and then being reflected down here. Half this light is then reflected upwards here, hit the mirror, and reflected downwards. So the original light was split into two different beams, which then recombined again before they hit this thing O here, called the interferometer. That should be, not interferometer. I'll fix it up. Interferometer. An interferometer is a device to measure interference patterns, and that's because, as we learnt way back in The World Communicates, that light waves can interfere with each other depending on whether they're in phase or out of phase. They can have constructive or destructive interference. And just like our analogy to the boats on the river, when different things travel at 90 degrees to each other on the river through that stream of water, they travel at different speeds. And therefore, if this experiment was travelling through the ether, experiencing an ether wind, which they assumed it was, that meant that this beam of light going up this way should be travelling at a different speed to the beam of light going this way. And therefore, even though they started off as all the same wavelength, all in phase light, when they travel in these different directions through the ether, they should have changed their speed, and therefore the light rays should have come out of phase. So this should have been out of phase with this, and therefore they produce an interference pattern in the interferometer. But it's a little bit more complicated than just that. So let's have a look over here, just to refresh my interference. So here's an example of interference. These two waves are completely out of phase, and therefore they basically cancel each other out as destructive interference. These two waves are in phase with each other, and therefore when they hit, they have constructive interference. So even though in theory M1 and M2 are the same distance from K, and I should have marked that on, I'm going to mark that on now. And we're going to say that this distance here, before I made that green, I should make that a different colour. Let's make that a bit black. This distance here and this distance here were exactly the same. So I'm going to draw some arrows on here, so just bear with me for a second. So that distance there and that distance there should have been exactly the same. We'll call that distance D. Okay, so this K should have been exactly the same distance from both mirrors, which meant that the light should have been travelling the same distance apart. However, light wavelengths are incredibly tiny, And even though they were trying to get these two distances as close as possible, there would always be some slight difference in the distance between this distance and this distance. And that meant that no matter how accurate they tried to be, by the time this light wave was split, traveled different directions and came back again, each of these two splits would have been traveling in a slightly different direction. So they were always going to be out of phase. So no matter what they did, they were always going to see an interference pattern, which at first might seem like a problem, because how can you measure the ether if they're already going to have different path lengths? So the path here would be we call that difference in path a path difference, which would give a phase difference. But according to the ether theory, not only would there be a path difference, there'd also be a difference in their speed, because they were traveling in different directions through the ether. And therefore you'd have a path difference which would get interference, but also this interference due to the ether. So there's two reasons why these two beams of light, the green beam and the purple beam here, would be slightly out of phase from each other. One, because of the path difference, and two, because of the ether difference. But this is where the genius of the experiment came from. They decided to rotate the apparatus through 90 degrees. And when they, on this big mercury bath here, as they rotate the apparatus through 90 degrees, one thing would change and one thing wouldn't. No matter where they rotated it, this difference in the distances would always be the same. And therefore that would produce the constant interference pattern all the time. But as we're changing these two paths' angles to the ether, just like in that boat analogy, if these two beams are traveling at different directions through the ether, their speeds will be constantly changing as they're angling different ways through the ether. And therefore, even though the path difference will stay constant, the speed difference due to the ether should be constantly changing. And therefore what they're expecting to see is, as they rotate the apparatus, this interference pattern would be changing all the time as these two light rays are traveling in different directions through the ether. So what they were looking for, and this is the key thing for the Michelson-Morley experiment, is that they result in a change in interference patterns. They were looking for, and that's what they were hoping to find, that as they rotated their apparatus, they'd see a change in interference pattern as the two light rays would be traveling in different directions through the ether. And that's the key thing to write down for that part of the course. Alright, so the Michelson-Morley apparatus was capable of detecting a phase change as little as 1/100th of a fringe. The expected phase change was 4/10 of a fringe, so the apparatus was much more accurate than required. And what they saw was, unfortunately, no matter what they did, no matter how many times they repeated the experiment, no matter how many times they rotated it, they got their interference pattern. That interference pattern was fairly constant because they knew there'd be a path difference in the light rays, but they expected it to change, but no matter what they did, the interference pattern did not change. So they had a constant interference pattern, there was no change. And that meant if the interference pattern wasn't changing, that meant the light rays weren't being interfered with by the ether, which was a bit of a problem. So let's write this down. It says, thus the result of the Michelson-Morley experiment was that no motion of the Earth relative to the ether was detected. The presence of the ether was neither confirmed or disproved. Basically, they couldn't find evidence of the ether wind. The experiment did not confirm or deny the hypothesis of the ether wind, and their results called a null result. A null result is where your experiments don't prove or disprove your hypothesis. But even though this experiment didn't prove or disprove the ether hypothesis, it was later used as evidence against the ether model when someone else came along with a different model for light that wasn't the ether model for light.